Welcome to today's lesson. I am Samasaka Kiyandens, and so I'm going to take you through a lesson on more concept, and so we go straight to the lesson. Well, as I've indicated, actually, today we're looking at the concept of more in chemistry. So actually, a more is defined as the Avogadro number of particles, that is Avogadro number of particles is 6.022 multiplied by 10 to the power 23. This is the Avogadro number of particles. So one mole actually is equal to the Avogadro number of actually particles in a particular substance. So it is actually of a chemical unit where actually it can be in terms of atoms, or it can be in terms of molecules, or it can be in terms of actually ions. So it does not matter. That's why I've said actually particles. Those particles can be atoms, or those particles can be molecules, or they can be actually ions. And so the mass of a substance that contains 6.022 times 10 to the power 3 particles of a substance is what is known as actually a mole. So what's important here is to know that actually it can also mean a mass. Okay, so a mole, it can be actually the mass of a substance that contains the Avogadro number of actually particles. Particles can be atoms, they can be molecules, or they can be actually ions in a substance. And the symbol that we use for a mole is actually M or L. Okay, so this is the symbol that we use for a mole, M or L. And so we said that since we said it can be a mass, so we can say that relative atomic mass, for example, of carbon, would mean that since the relative atomic mass for carbon is 12, we can say actually 12 grams of carbon atoms of carbon would contain actually 60 multiplied by 0 to 2 times 10 to the power 23 atoms. So in other words, what we are saying is that 12 grams of carbon would be equal to actually 60 on the 0 to 2 multiplied by 10 to the power 3 atoms. So in other words, in a relative atomic mass is equivalent to the number of actually atoms, which is equivalent to actually 6.022 multiplied by 10 to the power 23 atoms. Similarly, if you have 16 grams of oxygen, so 16 grams of actually oxygen would be equal to the same number, which is 0 to 2 multiplied by 10 to the power 23 actually atoms of actually oxygen. So it's very important to know that we can talk about it in terms of actually particles like atoms. So 16 grams is equal to actually 6.022 times 10 to the power 23 atoms of actually of oxygen. So these are also atoms of actually oxygen. And so one more, we can say actually one more, as we said, one more is equal to 6.022 multiplied by 10 to the power 23 number of actually particles. These particles which we said, they can be actually atoms, or they can be molecules, or they can be actually the ions. So this number actually 6.022 times 10 to the power 3 times is known as the Avogadro number. So this number, Avogadro's number, which is 0.022 times 10 to the power 23. This number is known as the Avogadro number. At times, it can be called the same number, can be called the Avogadro constant. This same number is also known as the Avogadro constant. And so we will go straight into a question. We see how actually we can apply these basic concepts that we have learned. What is the mass in grams of one atom of boron with the relative atomic mass of actually 11? And so here we know that since the relative atomic mass of actually boron is equal to 11, and therefore we can say actually 11 grams would be equal to 6.022 multiplied by 10 to the power 23 atoms. These are atoms of boron, because boron has a relative atomic mass of actually 11. And here the question is asking us, what about if there is only one atom? So if there is only one atom, we'll write the atom here, where there are atoms, what would be the mass? And therefore we can cross multiply this one. We can actually cross multiply for enable us to calculate. So we can say x multiplied by 6.022 times 10 to the power 23 would be equal to actually 1 divided by 11. Okay, and so our x is equal to, actually we can write it on the page. So in other words, what we said x multiplied by 6.022 multiplied by 10 to the power 23 would be equal to, actually we said 1 multiplied by 11. And therefore, for us to find x, would say actually is 1 multiplied by 11 over 6.022 times 10 to the power 23. And this actually gives us the mass actually to be, our mass would be actually 1.83 multiplied by 10 to the power 23, negative 23, actually grams. 1, which is equal to 1 atom. 1 atom of boron. So one atom of actually boron, as we indicated here. So one atom of boron, what is the mass in grams of one atom of boron? So in one atom of boron would be actually this mass, which is 1.83 times 10 to the power negative 3, 23 grams. And so we go to the second question. How many atoms of sulfur are there in 80 grams of sulfur? The relative atomic mass for sulfur is actually 32. So we can say 32 grams of sulfur would be equal to actually 6.022 times 10 to the power 23 actually atoms of sulfur. And so are there in 80 grams of sulfur. So if here we have 80 grams, this would be how many atoms is it going to give us? So we can cross multiply, and what we are going to have is actually 32 multiplied by x is equal to 80 multiplied by 6.022 multiplied by 10 to the power 23. And so we set 32 times x. So this one would give us 32 multiplied by x is equal to actually 80 80 multiplied by 6.022 times 10 to the power 23. And therefore our x will be equal to 80 multiplied by 6.022 multiplied by 10 to the power 23 divided by 32. And this actually gives us the this gives us actually 15.055 multiplied by 10 to the power 23 atoms. If we are to write it in actual standard form, to be 1.51 multiplied by 10 to the power 24 atoms. And we know that actually in 80 grams of sulfur, we are actually going to have this number of atoms. And so the last part of the question is actually asking us that we find the number of moles. How many moles of atoms are there in 50 grams of tungsten atoms? The relative atomic mass for tungsten is actually 180. And so we can say, since the relative atomic mass is actually 180 for tungsten, 184 actually, as we are given here, it is actually 184. So 184 grams as the relative atomic mass actually for tungsten. Which should be equal to this number of particles, 6.022 times 10 to the power 23 atoms. So what it means is that we are saying, what about if we have 50 grams? What is it going to give us? And so we know that X multiplied by 180, if we cross multiply, would give us actually 6.022 multiplied by 10 to the power 23 multiplied by actually 50. And so this will give us, we can make actually X substitute formula. And so what we're going to have is actually X is equal to 6.022 multiplied by 10 to the power 23 multiplied by 50 divided by 184. And therefore, the number of atoms, those here now we are calculating the number of atoms we are going to get. The number of atoms will be actually 1.636 multiplied by 10 to the power 23 actually atoms. But the question is actually asking us to calculate the number of moles. Now that we have found the number of moles, so we atoms, so we can say 1 mole is equal to 6.022 times 10 to the power 23 atoms. What about if you have 1.636 times 10 to the power 23 atoms? What is it going to give us? And so we can now cross multiply. We can say X multiplied by 6.022 times 10 to the power 23 would be equal to 1.636 multiplied by 10 to the power 23 multiplied by 1 if we multiply this one. And so we can get our value of X here, which is equal to 1.636 multiplied by 10 to the power 23 multiplied by 1 divided by 6.022 times 10 to the power 23, which actually gives us the, here that this one can cancel that one, and therefore what we find is actually we're going to have 1 0.636 divided by 6, which is equal to actually 0.272 moles. So this is actually what we get. We get that the number of moles, 50 grams, 50 grams actually, 50 grams or tungsten. 50 grams, so we're going to have 0.272 number of moles. So I thought today we can look at how we can use actually Avogadro constant. In particular, we have looked at actually the number of atoms in a substance. Next time we'll look at actually the number of other particles like molecules and ions. I thank you.